Pluto is not the dead, frozen rock we dismissed it as. For decades, we called it a relic, a leftover from the formation of the solar system, geologically dead, scientifically uninteresting. We stripped it of its planet status and stopped paying attention. Then, in 2015, a spacecraft crossed 5 billion kilometers of space to look at it for the first time. And beneath the surface of that frozen, forgotten world, the data suggests something that should not be possible. A liquid ocean that has never once frozen. What else did we get wrong? Pluto was discovered in 1930 by a 24-year-old astronomer named Clyde Tombaugh, working at the Lowell Observatory in Arizona. He found it using a device called a blink comparator, a machine that rapidly alternated between two photographic plates of the same patch of sky taken days apart, so that any object that had moved between exposures would appear to jump back and forth against the fixed stars. For more than 75 years, it was the 9th planet of the solar system. It had a name, a symbol, a place in every schoolroom poster, and exactly one known moon, Charon, discovered in 1978. But by the early 2000s, the picture had started to change. Astronomers were discovering dozens of other icy objects in the outer solar system, all orbiting in the same distant region, the Kuiper Belt. Pluto, it turned out, was not a lone outpost. It was the largest member of a vast, crowded population. In 2006, the International Astronomical Union reclassified it. Pluto became a dwarf planet. Most people concluded there was nothing more to say about it. They were wrong. On July 14, 2015, NASA's New Horizons spacecraft made its closest approach to Pluto, passing just 12,500 kilometers above its surface at a speed of 50,000 kilometers per hour. It had taken 9.5 years to get there. The first high-resolution images came back slowly over the days and weeks that followed. And with each new image, the same question kept appearing in the data. How? Pluto has mountains, not small ones. Ranges of water ice peaks rising 3,500 meters above its surface, comparable in scale to many peaks in the Rocky Mountains. On a world with no tectonic plates and no internal heat source we could account for, there should be no force to push rock upward. Alan Stern, New Horizons' principal investigator, had spent 25 years fighting to reach this moment. When the mountains appeared on screen, he later said he felt as though the universe had just become a much larger and more interesting place than he had thought it was the day before. That is not the language of a scientist confirming a hypothesis. That is the language of someone who did not expect what they were looking at. But the mountains were only the beginning, because directly next to them was something stranger still. Adjacent to those ice mountains lies a vast, bright region informally named Tombaugh Regio, after Pluto's discoverer. Its western half, called Sputnik Planitia, is a basin roughly 1,000 to 1,400 kilometers across, filled with nitrogen ice. Smooth, featureless, divided into irregular polygonal cells separated by shallow troughs. Those cells are not random. They are convection cells, columns of slowly churning nitrogen ice rising from below, cooling at the surface and sinking again. The same process that drives weather patterns on Earth. But on Pluto, at minus 230 degrees Celsius, nitrogen ice moves like a glacier in ultra-slow motion, turning over on timescales estimated at hundreds of thousands to millions of years. This surface is geologically active, right now, on a world nearly 40 times further from the Sun than Earth, and almost 1 billion miles beyond Neptune's orbit. The question nobody has fully answered: where is the heat coming from? Pluto has an atmosphere, a thin one, surface pressure roughly 100,000 times lower than Earth's, but a real layered atmosphere of nitrogen, methane, and carbon monoxide with complex organic haze layers stacked up to 200 kilometers above the surface. New Horizons watched it from behind. As the spacecraft passed into Pluto's shadow and looked back toward the Sun, it captured the atmosphere backlit, a series of blue haze rings glowing against the darkness, hauntingly similar in structure to the hazes that surround Saturn's moon Titan. That haze is produced when ultraviolet light from the distant Sun breaks apart methane molecules, which then recombine into complex organic compounds called tholins, the same reddish chemistry that colors much of the outer solar system. On Pluto, those tholins rain down onto the surface, staining it in shades of rust and brown. Pluto is, among other things, a chemistry laboratory operating at the edge of the solar system. Think of it this way. You are looking at a world the size of Russia, 4 billion miles away, that we dismissed as inert. And yet, it has weather, it has geology, it has chemistry rich enough to paint a landscape in reds and browns. Every process we associate with a living, dynamic world, Pluto has a version of it, not a pale imitation. Models of Sputnik. Planetia's formation suggests the basin was created by an ancient impact, a collision so massive it excavated a depression hundreds of kilometers wide. That impact should have left Pluto unbalanced, its heavy side gradually rotating away from the direction of Charon. The calculations show that it did rotate, and the direction it rotated implies that something heavy was already present beneath the surface, something that shifted the planet's center of mass toward the impacted region rather than away from it. The most consistent explanation: a liquid water ocean, buried beneath the ice, persisting in the dark for billions of years. Not frozen. Liquid. Kept warm, perhaps, by the decay of radioactive elements in Pluto's core. Possibly mixed with ammonia, which acts as antifreeze at extreme temperatures. No one has confirmed it, but the physics points there, and it refuses to point anywhere else. Not every scientist is convinced. Some argue the rotation data could be explained by variations in ice thickness alone, without requiring liquid water. The debate is ongoing, but here is what is not debated. Pluto is geologically active, atmospherically complex, and chemically rich in ways that nothing in our models of small frozen bodies predicted. The world we dismissed is the world we understand the least. Alan Stern has spent more than 25 years of his professional life on New Horizons. The push for a Pluto mission began in 1989, but multiple proposals were conceived, revised, and cancelled throughout the 1990s before New Horizons was finally approved in 2001. It was then nearly cancelled in 2002 when NASA's budget came under pressure. Stern fought for it each time. The spacecraft launched in January 2006, more than 15 years after the first serious proposals. On the morning of July 14, 2015, Stern sat in the mission control room at the Johns Hopkins Applied Physics Laboratory as New Horizons made its closest approach. The spacecraft was operating autonomously. There was no way to send it commands in real time across the 4.5-hour signal delay. All they could do was watch the telemetry and wait. When the first clear image of Pluto's surface came back and the team saw mountains, real, tall, geologically young mountains, Stern later described what he felt as a sense that the universe had just become a much larger and more interesting place than he had thought it was the day before. New Horizons is still moving. After its Pluto flyby, NASA extended the mission. New Horizons is now more than 9 billion kilometers from the Sun. It will continue transmitting data until the late 2030s, when its power source finally fails. Out there in the dark, New Horizons is still moving, and Pluto still has secrets we have not thought to ask about yet.